Okay, just looking back then, what we've got is our proof from our original particle. If you need to know your way around this fully, okay, so if you're asked to do the full derivation, it's rare, really rare, more of an AQA thing. But if you would need to know your way around this, then what I suggest you do is do this in terms of a flow chart. So the steps are just being a little bit careful, like that, making sure you actually don't just put rate of change of momentum and subtract them, but actually which second one subtract the first one, final answer versus subtract the initial answer. And then the rest of it is all about that flow chart. So what you're finding is you're on the impulse and time between collisions, okay, divide by time between collisions. Okay, that goes to the idea of, excuse me, terrible error, force, okay, because it's rate of change of momentum. That gives you pressure, and then that is effectively the whole thing, but we can simplify it to rearrange it to pressure volume, because that's kind of convenient. Then you go into for the realistic bit. Okay, so what we've got is you then multiply by n. Then you go into average particle. I'm going to add a little bit of a hint on this one. And then what you've got is from that, with your average particle, you then substitute together. So that gives you final PV equals a third nmc squared bar. You don't need to get tied up about negative and positive. You can just say for the pressure on the wall is, and just give that last stage, so you can ignore that. Little cheating, but it's not untrue. Now, it's going to pick up on this bit here, okay? If we think about, try and get it all in the same picture, if we think about this, what is this saying when we put this in? Well, we're saying that the velocity of your average particle, they have speeds, okay? Squaring them gives you kind of mean, but a third of them are going in the x direction, a third of them are going in the y direction, and a third of them are going in the z direction. So effectively, you could cheat slightly, and just say a third in each direction. Okay, so we could do a little bit of cheating because you've got fairly straightforwardly that from that first stage here. Okay, so you've got these, and then you could just go, right, we're a third of them are going in each direction, so I'm just going to change that to general C rather than a V in the x direction, and a third. But don't just do it, say that. Okay, so state your assumption, and that's a way of cutting some corners. Okay, so that's a way of cheating ever so slightly. However, the most common thing is actually using this. Okay, so we've got our equation, that's on your data sheet, so that does give you something to aim for as well. But the most useful bit is actually, well, where does this come from? We've got c squared, so if we need to think about these, and pressures and volumes and masses, we can easily do that, but the c squared is kind of a bit of an awkward one, because we actually can't see the particles, so how are we going to find that? So the final bit is the one that they think about all the time, and introduces a phrase that makes it so much easier in your descriptions. Rather than talking out the root mean squared velocity, we can just talk about the mean, or average kinetic energy, and that is a really useful phrase to just use in your descriptions. Okay, so it's actually nice and straightforward, and this bit is definitely you need to remember. So if you found that first derivation to get to the equation difficult, this one's much more straightforward. Make sure you use it. Okay, make sure all of you learn this. Those going for the higher grades, learn both. Follow the thought process. You'll find it very useful as you go on to university. It's all about that logical process, okay? Flow charts and everything. So, what we're doing here is we're merging the two theories. So what we've just done the kinetic theory, thinking about the kinetic motion of the particles, and then the empirical, i.e. measured, equations of state. Okay, so that's practical. That came from the 1800s, and this one came from the 1900s, so this is much later, about 70, 80 years, possibly more actually. What am I talking about? 1700s, this one. So yeah, about 100 years later. Okay, so if we merge them together, it's nice and easy because, strangely enough, they both have, and they're both in your data book, they both have PV in. So from the one that we've just done, a third NMC squared bar, that's your kinetic theory, and it's going to equal your equations of state of a large amount of gas, nRT. Okay, and I'll just put equals PV again, just to make it easier. Okay, so nice and clear. So we can obviously make them equal. Now if we do that, then we can simplify it down a little bit, and the way to do that is we're talking about the kinetic energy itself. So if we're thinking about the kinetic energy, I'm just going to change this as we're going along. Okay, we're actually talking about internal energy, so that equaled the U in our original equation. Okay, so that's that bit. Not important. Stick with the kinetic energy. Well, that's going to equal half m. We've gone to c, so c for our root mean square velocity, that. If we want the total energy of all of it, then I just need to multiply it by the number of particles we got. Okay, so quite similar looking equation, so it's not hard to remember what that step is. It's just kinetic energy. Again, please notice kinetic energy equation isn't on the data sheet for anything, so you do need to remember half mv squared. Here we're talking about c bar squared to give us that RMS value. Okay, and what we can do is simply then say, well, what we've got from up here is nmc bar squared, okay, is going to equal half multiply, I'm missing out a step here, just warn you, nmc bar squared on its own, okay, is going to be taking the 3 across there, equals 3 nRT. Okay, multiplied by. So what we end up with is 302. Little n, I should point out, little n RT, because that's a molar gas, a mole of gas, or how many moles of gas, the molar gas constant and the temperature. So that is basically equal to your average, or mean if you prefer, average kinetic energy. Oops, sorry, I can't spell kinetic N. Oh, I was right. So, again, just try and ignore that page underneath. Let's hide that to make it clearer. There we go. So that's average kinetic energy. Excellent. Of moles of gas. Chemistry use that level. Again, we're going smaller because we want to know about individual particles. So actually, if we put those values in, okay, and think about that, then what we can do is we can substitute that and go into there. So I'm gonna just put it as E average, okay. Let's make it and what we're going to have is 3 over RT 2 NA. Okay, so if we put that in, what I can do is substitute. Start that again. So if we think about the ratios, what NA is, NA, I've missed out a step here, is the total number of particles, okay, divided by the number of moles. Okay, so what I can do is substitute both of those in. So N over, and what we're going to end up with is a large number where you're effectively putting in, and let me just say that, we're multiplied by N. So effectively what we're going to do is come up with 3 over 2 KT. And I think, trying to think on my feet, I've made a mock-up of that somewhere. That doesn't look right. Substitute it in yourself. You'll be fine. But the bottom line is the energy, okay, is really, really, really simple. The energy of a gas, Okay, the average energy of particles is simply down to its temperature. So if we go back to those gas laws, PV, great, all that behaviour depends on the mass and the kinetic energy. Well, the kinetic energy is all about its temperature. That's the only factor that goes into it. So when we're talking about average kinetic energy, we're actually talking about KT, because that's 1.5. Okay, those are hundreds usually. Those are times 10 to the minus 23. That's a really, really small number. We're not worried about whether it's 1 or 1.5 times. So basically, around about KT is the average energy of a particle. But if we link it back to those, I'll just squeeze that in. Again, that distribution, that's a terrible graph as well. Sorry, I'm a bit of a slope there, and it doesn't go up. Down here, that's your average energy. This is around about 15 to 30 times average energy. Okay, so big idea, and we're going to leave it there for today. Learn your way through that proof, okay? Right guys, so I split that video into two and just finish that chapter with the hardest bit. So again, in your mind, you already knew that because from Key Stage 3 you've been doing about this for a long time. This is what particles in the gas do. Well, we've just proved that they do, and that was through Boltzmann's proof. So all the stuff in the first part of the chapter, just bear in mind, okay, all of this stuff here, this is all the empirical gas laws. Okay, so PV is proportional to T, and you can multiply by a constant to get PV equals nRT or nKT. Usually nRT because it's a quantity of gas. Okay, we are not talking a gas with tiny little numbers like that. That, if we multiplied out by realistic amounts, would give us a statistical thing, which is the kinetic theory stuff. So this is all the theory, okay, and these ones are all the empirical, done by measuring. I don't know where the word comes from. I don't think it's anything to do with empire, but there we go. So you already had that in the back of the mind. This is why I kept doing mentioning particles, but actually keep it just on those PV and T calculations, or specific heat capacity, specific latent heat. Okay, thinking about it as a lump of stuff rather than particles. But in your mind, if you can make those pictures happen, that might make it easy to understand what those things represent. You won't be asked that, but it's really powerful to have those ideas. And if you go on to higher level physics engineering, you'll need to be able to make that link much more frequently. The second bit is where a lot of the questions come in. So most gas questions tend to have a bit of everything. They'll tend to ignore specific heat capacity and latent heat, but they will have those as separate questions. Okay, so they may be multi-choice questions, for example, but these, the full questions tend to be about these. So even with the derivation, if you can, that's great, but put all the ideas together, practice. So make yourself a nice big picture, so you've got this mental picture of how it all works. Link the gases, definitely that one. Okay, maybe, say, if you know your way around, it's not hard to make that link. Okay, so that's your link derivation. But basically, yeah, know your way around that second derivation and understand the concept of what that means. Then practice. So all the slop is there. All my deeper questions are in the back here, down to the thermodynamics second law, stupid Robin, etc. So have a practice on those, and the bits at the back, as I say, there are loads there. This is mainly extension, but it kind of drives it down. So anything up to question 30, up to 31, sorry, these are really typical questions. Okay, so really get your head around that 14.5 section, and then there's a shed load of practice I'll put into Teams as well. Okay. Good luck with that, guys. You will get that in your test, so know your way around it.